Well, we've been talking in class today about the extinction paradox. The extinction paradox was that if you have a large particle compared to the wavelength, it seems to remove twice the amount of power that is incident on it into the scatter power, which would mean that the scattering efficiency of such a particle is actually 2, and which would imply that the scattering cross-section of such a particle is actually twice the geometrical cross-section. This seems a little bit paradoxical, of course. It goes a little bit against your intuition that the particle should remove twice as much as light as that is incident on it. It is truly a paradox. The classic, so to say, way of explaining that originates to van der Hulst. And in order to explain what is actually going on, we need Babinet's principle. The principle of Babinet states that if we have a hole of a certain size which diffracts light, so you have light incident here from the left, and light is diffracted here on the other side of the hole. If you would now take a particle that has exactly the same cross-sectional area as the hole, so let's place that here, and we would have light incident here as well. Then part of the light will go straight through, of course, and part of the light will be diffracted around the edges of this particle as well. Now, if you would remember that the particle, the screen here has the same dimensions as the hole, so if I would put the screen in the hole, I would have a superposition of these two states, which means, of course, experimentally, it would be dark on the right-hand side of the now full screen. So that implies that the diffracted fields from the hole and from the particle have to be equal and opposite in phase, so that they cancel each other. So if these fields are identical in amplitude, opposite in phase, that means that their powers are equal. So the power diffracted by an object is equal to the power diffracted by its projection. So this is Babinet's principle. So now let's apply that to a particle of arbitrary size. So we have let's say a water drop, which is big compared to the wavelength. We have 3 effects going. We have light that is, for example, directly reflected from its surface. We can have light that is refracted inside, like this, for example, forming a rainbow. And because of Babinet's principle, we have light that is diffracted across its edges. For the light that is incident on the particle, that exactly sees the area of the particle. So the cross-section or the efficiency for diffraction, for refraction and reflection, so let's call it RR, is equal to 1. But based on Babinet's principle, the diffraction, the power diffracted by this particle has to be the same as the power diffracted by a cutout of the particle. If you make a screen that exactly fills the particle, and that is also 1. So the diffracted efficiency for diffraction is also 1. The sum of which is 2, the total efficiency. So there we have total is 2. There we have the extinction paradox. Now there is a problem associated with this because, as van der Hulst says, if you would put a flower pot in a window, that would not appear to block all the light. It would just cast a shadow exactly in the size of the flower pot. So it would seem that the scattering efficiency or the blocking efficiency is only 1. Van der Hulst explains this by saying, okay, this diffraction pattern can only be observed in the very, very far field. So for example, if I would take that flower pot and send it into outer space, have it illuminate with a very distant star and pick up the light with a telescope, then, only then, indeed, I would see that twice the amount of incident power is blocked. That seems elegant enough, but there is only one problem. From Maxwell's equations, we can actually demonstrate that it should not matter where we make this analysis. So if you would make this analysis very close to the flower pot, it should give the same answer. So the paradox apparently still stands. There is another explanation, which is due to Keller, which uses actually very similar arguments, but does not rely on this diffraction pattern. It goes like this. So let's say we have a particle that blocks light. So we have incident light here. Part of the light just passes through. Some of the light hits the particle and gets reflected or refracted. Let's draw it just like this. And so again, the efficiency for reflection and reflection is 1. Now let's take a closer look at the incident situation where there was no particle at all. In that case, we simply would have a field that looked like this. Now, Keller defines the scattered field simply as the total field minus the incident field. So if we look at the total field here in the experiment and the incident field over there, then we can draw up the scattered field. So let's take the total field and subtract the incident field. This way would cancel, this way would cancel, this would cancel, this one would cancel. So we are left here with no rays at all, no rays at all. But here, just at the position of the particle, subtracting the incident field from this total field, in that effect, this part will be left. And again, this is the reflected part, which has an efficiency of 1. All the light that hits the particle is reflected and reflected. Here, after the particle is dark, so that means that if I subtract this incident field from the total field, I need an extra contribution that is opposite in phase, but equal but carries equal power in order to effectively cancel the light, so that I end up with zero power detected here. This contribution obviously sees the same geometrical cross section. So here, for that part, what Keller then calls the shadow forming beam, so let's call that SFB, the efficiency is also 1. And again, adding that up, it would lead to 2. An efficiency, a total efficiency of 2. Now, as you notice, this whole analysis was done exactly in the near field. So it does not rely on this concept that von der Hulst needed in order to explain the paradox. So no diffraction involved at all. Is this convincing? Is this satisfactory? Well, no, not entirely, because now it seems okay. The whole diffraction part is gone. Yeah. Okay, that could be. It could also be that it is inherently incorporated in this. The explanation that Keller gives is pretty rough around the edges. So I don't know. Also in the literature, there have been also some recent publications that try to explain the paradox in even with other methods. So I'm not even sure that it is that the paradox is actually resolved. So it remains a true paradox, I think. Okay, thank you for this. I hope this opens up some discussion. I will post some links along with this video, and who knows what comes out of it.